지금부터 피스바 포럼을 시작하겠습니다. 여러분 안녕하십니까? 세계평화의 날 기념 피스바 포럼 진행을 맡은 미래세대 학생대표 경희대학교 신재휘입니다. 지구촌 곳곳에서 들려오는 폭염과 한파, 가뭄과 홍수, 그리고 얼음이 사라지고 있는 북극, 이 모두 산업화 시대의 탄소 문명이 초래한 결과입니다. 오늘 모신 석학들뿐 아니라 유엔과 기후학자, 전문가들은 전시와 같은 전폭적인 대응체계가 필요하다고 말합니다. 그러나 세계의 정치권은 눈앞의 현실 정치에 몰두하며 적극적인 대안을 내놓지 않고 있습니다. 오히려 국제사회 일각에서 기후변화는 거짓이라는 기류를 만들고 있습니다. 학계와 시민사회가 적극적으로 기후변화 문제 해결에 나서야 하는 이유입니다. 오늘 피스바 포럼에서는 Save the Earth, Make the Future라는 주제로 석학들과 함께 우리 미래 세대가 기후 위기를 극복하기 위한 대응 방안을 심도 있게 논의해보고자 합니다. 오늘 이 자리에는 특별 강연 연사로서 케임브리지 대학 피터 어담스 교수님, 로마클럽 회원이신 이안 던롭께서 참석해 주셨습니다. 또한 경희학원 조인원 이사장님과 전 유네스코 사무총장을 역임하신 이리나 보코바 교수님도 참석해 주셨습니다. 먼저 오늘 여러분들께 특강을 해주실 특별한 두 분을 소개해 드리겠습니다. 피터 어담스 교수님께서는 케임브리지 대학교 교수이시며 평생을 북극 연구에 매진하셨습니다. 많은 박수 부탁드립니다. 다음은 이안 던롭 선생님이십니다. 던롭 선생님께서는 호주의 화석연료 기업에서 임원으로 활약하셨으며 이후 더 내셔널 센터 오브 클라이밋 리스토레이션이라는 싱크탱크에서 기후위기에 관한 연구를 수행하고 계십니다. 따뜻한 박수 부탁드립니다. 먼저 피터 어담스 교수님의 특별 강연이 있겠습니다. 여러분 힘찬 박수로 맞이해 주시면 감사하겠습니다.
Thank you very much. What I'm going to be talking about is the present state of the Arctic as far as climate change is concerned, and some of the consequences that are following from the fact that the sea ice and land ice are both disappearing. Tomorrow I'll be talking again mainly about land ice. So in this particular talk I'll concentrate on sea ice and what the consequences are of the loss of the sea ice for other aspects of the climate system. I'll end up by saying that in my view that we have to actually take carbon dioxide out of the atmosphere in order to save ourselves, because if we don't, we'll simply get warmer more slowly, even if we reduce emissions. So I've been recently visiting some of the labs where new methods are being tested out for doing this. So I'll show a couple of pictures of latest work in California on carbon dioxide removal. There's a foundation now in Britain led by Sir David King, which is called Carbon Repair. And the focus of that foundation is on taking carbon dioxide out of the atmosphere rather than simply reducing our emissions. So, let's see. This doesn't... Okay. So when we think about the Arctic Ocean, and I'm talking mainly about the Arctic Ocean here, it used to be something that had a very special place in people's thinking, both in Europe and in North America, in that it acted as a barrier to both as a barrier to transport. You couldn't do any shipping operations across the Arctic because of the ice, but also as a unifying element because all of the oceans in the world seem to be in the southern hemisphere, but in the northern hemisphere we had North America on one side, Eurasia on the other, but joining them together was something that was very similar to land, that is sea ice, and the sea ice was there continuously. So this is what we now call the old days, that is the time when I was starting out my research. Now this is too old a day. This is just not. Okay. In the late 20th century, and on the right-hand side, we have the way that the extent of sea ice during the winter in the northern hemisphere, and we can see that not only were the two great continents joined together, but the sea ice extended through a lot of the subarctic seas, like Sea of Okhotsk, Bering Sea, Hudson's Bay. So it really cemented together Europe and North America. And even in the summer, on the left-hand side, the sea ice still really filled the Arctic Ocean, and it was very difficult in a ship to be able to sail around the edge and get through the northern sea route, north of Siberia, or the Northwest Passage in the north of Canada. This is okay. Okay. This is not working very well. Okay, we'll start. Well, in the early days, before there were any powered ships around, this is the way that you had to try to explore the Arctic and get through the ice to try to get to places you wanted to be, to try to exploit a Northwest Passage to China or to do anything else. But the trouble was, with only sail power, you ended up for most of the year being stuck somewhere and possibly dying. The hope was that there were what drove people on. One of the things that drove people on was a completely bogus theory, which was held in the middle of the 19th century, called the open polar sea. And the idea was that if you pushed north through all the heavy ice north of Greenland and Spitsbergen, you would finally get through the ice and get into a wonderful open sea that would get you to the North Pole. How it's possible to have an open sea at that latitude, nobody explained, but the theory was eventually abandoned when it was found there wasn't such a thing as an open polar sea. So all the real exploration of the Arctic had to be done using proper Inuit methods of dog sledges, and that's how it was delineated that where the ice was. But still, it was clearly impossible to have any trade routes through the Arctic Ocean or even through the Northwest Passage. But that started to change in the 1950s as we started to see retreat of the sea ice. And this shows the bottom curve here is the summer season from 1900 onwards. And we can see that a retreat of the sea ice started in about 1950 and has continued ever since. The ice is retreating in other seasons as well, but the most rapid retreat has been in the summer. If we look at any given month of the year, we find that this trend has continued into the present day. So everywhere we look, the sea ice is retreating. Okay, until we reach the point by the early years of this century that the retreat in summer had reached such a large extent that we could now talk about an open polar, at last talk about an open polar sea. So here we have the Arctic Ocean on the left in September, with such a large amount of melt having gone on that half of it is now open water. And in 2012, this was the lowest ice extent so far in summer. And again, large amounts of open water north of Russia and north of Canada, to the point where you could reliably send ships through the Northern Sea route north of Siberia with very low expectation that it'll be stopped by ice. So we start to think about trade routes now in the Arctic. This tells, we can see that the ice was retreating from the data that we get from satellites, but in order to see how thick it is, you actually have to go underneath it and do measurements from submarines looking upwards. And we've been doing this now with the British submarines since 1970s, and the US has been doing the same. And scientists on submarines don't have a very good time, and so they're accommodated in torpedo stowage racks. So it's not the most comfortable way to do science. It was through the use of submarines that we first managed to show that the ice is actually getting significantly thinner. The left-hand picture here shows the left-hand picture shows the mean ice thickness in 1976, and the middle one shows the thickness in 1987, and the top right shows the thickness in 2004. We see a huge loss of average thickness. The ice is not growing as thick, and it's not getting as deformed by being pushed around by the wind as it was before the 1970s. So we found an 18% loss of thickness, and now there's more than a 50% loss of thickness between the early years and recent ones. This is a set of American data showing the difference between the early 90s and the late 50s for thickness in different parts of the Arctic. And we see the thickness has gone down by about 50% wherever you look. And if you take the thickness as going down by 50% and the area going down by 50%, the result is the volume of ice has gone down by about 75%. So this shows summer ice volume in the Arctic between the late 70s and 2011, and we see it's gone down to about a quarter of what it was. So that's a massive loss of ice volume. And that can be, you can picture that as called a kind of death spiral, where you follow the volume of the ice round the clock and see how it diminishes with time. So all of these curves for different months of the year are spiraling in towards the center. The rapidity with which the ice is going exceeds all the predictions of climate models, and that the black line here is the average of a lot of climate models that are used by Intergovernmental Panel on Climate Change, and the red line is reality. So we see that the Intergovernmental Panel is forecasting still plenty of summer ice around by 2100, but already we got down to those levels by 2012, and will soon be down to zero. The other thing is the ice is changing its nature. We have very little of this kind of ice left, called multi-year ice, that's many years old. This used to be prevalent when I was first starting out. It's pretty rugged type of ice to try and travel across. And now it's much thinner and easier to traverse. It's also much easier to break, so that unfortunately it makes it easier to do oil exploration, because drilling ships like you have on the left here need to be kept in position by icebreakers breaking up the ice around them so they're not pushed off station, and that's a much easier thing to do now. Other things are more difficult than in the past. We used to do experiments on ice stations where you would set up ice camps like this for several months and sit on the ice and work on the properties of the ice and the ocean. These camps were maintained and established by air, but you can no longer rely on the surface staying put for the winter months. This is what you get now. This is the middle of winter in 2013, and we see this pattern of cracks and leads due to the ice breaking up because it's so much thinner than it used to be. So you can't safely operate an airstrip on ice anymore, and if you want to work on ice, you have to do something else, like work from a ship. So that's what we see, but the retreat of the ice has impacts which are far exceed the actual ice nature of the ice itself. They extend into other aspects of the climate system, and these are a few of them, and I'll just quickly deal with them. But they mainly consist of that the retreat of sea ice then affects another element of the climate system in a positive feedback to make the effect worse. So, for instance, albedo feedback is where when the ice retreats, an area that used to be ice covered, that's in the bottom picture, we see then and now pictures, with the blue being areas that are now free of ice in the summer, and were then in the past were not. And you're replacing a surface which is white, which would be reflecting in winter 80 or 90% of the radiation falling on it, and replacing it by open water, which reflects less than 10%. So there's a massive change in the amount of energy reflected back into space. Now that's already, in this study by Pistone, they reckoned that it's equivalent to adding a quarter to direct greenhouse gas forcing. That is, you create carbon dioxide, release into the atmosphere. The amount of warming that you get is actually 25% greater than you would get from the direct effect of the CO2, because the CO2 causes warming of the climate warming causes the sea ice to retreat, the retreat of the sea ice decreases the albedo of the planet, and the planet absorbs more heat. So this 25% factor, we've just shown in a paper in Nature that in fact you should be using 40% instead of 25%, because on top of the retreat of sea ice, you've got a retreat of snow on land. The snow lines around the Arctic are retreating very fast, so areas that you always thought of as snow-covered forever, like Alaska and northern Siberia, are actually now snow-free. So this is the snow, how the anomaly in snow area has changed over the last 30 or 40 years. We've now got a 6 million square kilometre negative anomaly. And that's enough. And you add the snow and the ice together, we get this 40% enhancement of warming. The second effect is the fact that with the water being open around the Arctic Ocean in summer, you get warmer air moving over the Greenland ice cap and causing the surface of the Greenland ice sheet to actually start melting. This never used to happen. And I'll go quickly over this because I'm going to talk about this some more tomorrow. Having just come back from the Greenland ice sheet, I'll be able to show some pictures of what's happened to it. We know that from gravity satellite missions that the ice area or the ice volume in Greenland is decreasing more and more rapidly, and that's releasing a huge amount of water into the ocean and is now the chief cause of global sea level rise. So the coupling of Greenland ice sheet retreat and global sea level rise is a very strong one, and of course the difficulty is if we want to do something about it, how do we deal with Greenland ice sheet retreat? A second problem is methane. The Arctic Ocean, as you can see, a third of it at least is shallow water, less than 100 meters deep. The rest is very deep ocean water. And in shallow water, with ice-free conditions in summer, the water warms up. And when it warms up, you can get quite significant temperatures in summer. On the left, you're getting 5 degrees north of Siberia, and I've measured 11 degrees, which is quite, you could swim in that. What that does is it thaws out a protective layer of permafrost on the seabed and reveals the existence of a thick layer of sediments that are contain methane. And this is what they look like, called methane hydrates. It's ice with containing methane gas, and the ice crystals contain methane. So, in fact, if you apply a light to this, it burns, and it's quite eerie. And there's a very nice film out, which I recommend, called Ice and Fire, produced by Leonardo DiCaprio, in which they show some very nice film of people setting fire to themselves accidentally by standing on frozen lakes, cutting a hole in the lake, and then methane's coming up from below. And this is the sort of thing that happens. The methane comes up in big plumes, and this is increasing the methane content of the atmosphere quite significantly. And these are methane bubbles sitting against the bottom of the ice. The threat there is that with this protective layer of permafrost being melted, you could get a huge methane outbreak, and that could cause a very large, quite sudden increase in global warming. We calculated it could be 0.6 of a degree just within a year or two if about 8% of the methane in the Siberian Sea comes out through abandonment of the protective layer. And we can see the methane in the atmosphere starting to rise. This is a measuring station in the north of Canada, where the red is the last couple of years, and we see that the methane content is taking off. Now, the Arctic is warming much more rapidly than other parts of the world, and this adds to the effect that you're getting a 2 or 3 times factor of multiplication for warming. And this has impacts on weather events, and this is one of the other big things that we're suffering from at the moment, that the jet stream, which is the brown area here, which is the wind system separating polar air from tropical air, has slowed down recently because the Arctic has warmed faster than the tropics. The temperature difference is getting less, so the heat transport is less. So we're getting a slower Gulf Stream, which tends to go into these large lobes, just like a slow-flowing river goes into large lobes. And the large lobes mean that you can get polar air coming down to latitudes where it shouldn't be, and tropical air going up to high latitudes where it shouldn't be. And the result is the sort of extreme weather uncertainties that we've had. those events have an impact, a very bad impact on the planet, because they occur in the latitude range where most of the world's crops are grown, in North America, Europe, Ukraine. And if you're going to have crops upset by extremely cold or extremely hot conditions, that's going to reduce our food production just at a time when our population's also going up. So I wanted to end quickly by saying, what can we do about all this? And my feeling strongly is that we should go for taking carbon dioxide out of the atmosphere. And that's the view of this foundation, which was established in California last year, and its British branch is run by David King. And it's called climate repair. And we want to repair the climate, that is, take it back to a livable state by removing CO2 from the climate. That way we're reducing the greenhouse effect directly. We're not letting the greenhouse effect get gradually worse, which is what would happen if all we did was reduce our emissions. So the trouble is, it is getting worse at the moment. This is the level of CO2 in the atmosphere. There's no sign that any of the actions which the world agreed to take at various times have actually done anything to reduce the rate of increase of CO2 in the atmosphere. So I'm having to skip a few things here because this system's not working too well. So here's what we can do. First of all, we can slow the rate of warming by doing things that can reflect more heat back into space. And one of my favourites is this one here, developed in Scotland by Stephen Salter, who's a very good engineer, in which you pass very finely divided seawater particles out into the bottoms of marine clouds, and this makes them brighter, increases their albedo, and it cools the climate. And you can operate using a large number of drone-type ships, and you can cluster them around places where you really want to cool the climate down. And one of those would be the Arctic, to try and stop the ice from retreating so fast. So that's called geoengineering. That's using engineering to increase the amount of reflection of energy from the surface. But the other thing is direct air capture, and this is what, in the end, will save us, I think. And also, if we get this machine to work. Direct air capture is where you actually take carbon dioxide out of the atmosphere by chemical means, passing air over an absorber, and then you have the product has to be gotten rid of. That's the problem. If we're going to do this as our main means of controlling climate, then we have to take over 40 gigatons of carbon dioxide out of the atmosphere per year, which is a massive amount. And if we don't want to produce a product which just piles up like a kind of a great pyramid every year, we have to use it to produce something where the world needs 40 gigatons of it. There aren't many things like that, but one thing is sand and concrete and cement. That's about the only product which we use that kind of volume of. And I'm afraid this thing is just not working. Okay, and I've been visiting laboratories which are doing this, and one of the very promising ones is called Blue Planet Limited in Los Gatos in California. And what they're doing is they take the carbon dioxide out of the atmosphere chemically, but then they have a further chemical reaction in which they turn it into artificial limestone. And this is the limestone comes in this size of lump, and they can then incorporate that limestone they can grind it up to make sand for for cement production or road building, or they can incorporate it into concrete aggregates, and that gives you a concrete which is carbon negative. So here, if this thing will work, okay, it doesn't. Okay, here's the concrete. Here's a concrete aggregate in which these lumps of artificial limestone are incorporated in the concrete. Concrete is a terrible material because to make it uses a huge amount of energy because the chemical reaction and the energy that you need to make the concrete combine together to make concrete one of the worst things you can use. I mean, we shouldn't be building buildings out of concrete. So it's a horror to see huge apartment blocks made of concrete. But here's a case where you can get a concrete which is actually carbon negative by incorporating large amounts of this material that has been taken out of the atmosphere by chemical means. It's being done here in California, but also there's a plant in Iceland which doesn't do concrete but puts the carbon dioxide underground. And so you have to find a way of dealing with the product as well as getting rid of the carbon dioxide at an economic rate. So this shows the aggregate. And then this is other techniques that they're trying in America, is taking agricultural waste and turning that into energy via a process called pyrolysis, which produces a kind of carbon material called biochar, which has some useful properties in agriculture and produces energy as well. So the raw material here in the plant that we were looking at in Bonaventura is actually pistachio nut shells. So you can save the world by using pistachio nuts, but in California that's a significant product. And this is the biochar converter, which is a mobile one, and you can have hundreds or thousands of these around all the fields of California, taking agricultural waste, producing energy, and producing this biochar product. So there's another approach. So there's a lot of these being done, and everybody who's doing them is very enthusiastic, very energetic. This is the same place, the university here in the California University in Ventura is converting to using biochar. So that's their product. So they're always very keen. They always need money, and everybody that I talk to seems to need $2.1 million. This seems to be the number that they need to make significant progress. So there's a very sad. It's very good to see this wonderful effort being done, but it needs to be not starved of funds. It needs to. The people who are doing this need the money to be able to take these ideas and turn them into reality that can be scaled up to save the world. I mean, literally, the concrete method, if it can be done cheaply enough, would literally be able to save the world because it produces a product that everybody needs and therefore is not going to be limited by the problem of scaling. So I think there's a lot of hope for saving the world's climate, but only if we're going to take this path, this is the one in the long run that would lead us to a climate that can be lived with. Anyway, so we've gone quite a long way from the Arctic here to Southern California, where I was last 2 weeks ago. But that's the path that a lot of people take when they start thinking about this problem. Okay, thanks very much. I'll.
교수님 감사합니다. 피터 다음스 교수님께 다시 한번 뜨거운 박수 부탁드립니다. 이어서 이안 던럽 선생님의 특별 강연이 있겠습니다.
Okay, well, thank you very much indeed for the invitation to speak with you this afternoon. What I'd like to talk about is climate change in the way that I see it, which is an immediate existential risk to the future of humanity. And what I'd like to do is I'll explain that as we go through, but that's the focus of what I essentially have to say. Okay, well, the first thing I'd like to touch on is the fact that climate change is only one amongst a number of major problems that the world is faced with. This reflects the Limits to Growth report that the Club of Rome wrote in 1972, which tried to look at the implications for humanity if economic growth and population growth continued in exponential terms. Where would we end up? And what it shows, I won't get into the detail of these lines, but you see the growth in all the key issues we are accustomed to discussing, the increase in food per capita, services, and so on, and the number of non-renewable, Put the next one up. Okay, the number of non-renewable resources declining. You can see population growth growing and so on. That all continues, and until you reach that point round about now, where things start going over the top and turning down, where effectively we don't have the resources to continue to supply population growth and economic growth as we've known it historically. This work was done in 1972, the first ever time that a computer model was used to predict the way in which these issues might emerge globally. The remarkable thing about it is that if you actually look back at what has happened since 1972 and today, those trends are almost exactly what has occurred in actual fact in terms of economic growth around the world and use of resources. The problem is when you reach around about now, 2020, 2030, things start breaking up and we can't sustain the system. Now, the biggest issue in this is in fact pollution, which was the proxy, if you like, for climate change. And what we're now seeing is that unless we fix climate change, then we can't continue to sustain the development of the economic system in the way we've known it. But apart from that, we then have these other issues that also have to be addressed. So we are going to have to think about economic growth, whether that's possible, the way population has been growing, and a whole host of other issues. I'm happy to talk a bit more about this in the question and answers afterwards, but for the moment, just reflect on the fact that there are many other factors that we have to determine apart from climate change. So we have exponential growth in a finite system. Our civilization, as we know it, only works if you have that growth. But the trouble is that it's now destroying the resources that actually maintain the civilization as pollution increases and so on. So that, the question then is, well, how are we going to resolve this dilemma? And that's what I'll talk about a bit more on the climate front. All right. Could you move the slides along, please? Okay, you do it. And the next one, please. Keep going. No, back. Back. No, back the other way, please. Back. Sorry, we have to go back again, please, to the white slide. Here we are. That's it. Oh. Next one. Okay, so what I'll talk about is population growth briefly. Secondly, climate change, energy risk, and basically solutions in that order. Okay. So if you talk about population growth, we're now at a quite remarkable point in human history. What you've seen is a massive increase in population basically since the early part of the century, particularly since the end of the Second World War, 1945, we had a relatively empty world. Now we have pretty much a full world of around 7.7 billion. The question is, where are we going to go to? The UN forecasts that we will reach, say, 10 or 11 billion, but with the constraints we're now faced with, we may not actually achieve that at all, and we may end up leveling off to somewhere around 8 or 9 billion. Okay. Now, the only reason the population grew in that way was actually with the availability of cheap fossil fuels. If we had not had coal, oil, and gas, we'd never have seen population increase. And whilst we're now critical of the implications of using fossil fuels, they have delivered tremendous wealth to the global community, and we shouldn't forget that. But the trouble is, those fuels are no longer cheap and they're no longer sustainable. You've had too much of a good thing, and therefore we now have to move away from them. Now, climate change then is happening faster than anticipated, as Peter has already mentioned. It's primarily driven by human carbon emissions from fossil fuel consumption, agriculture, and land clearing. And this is a picture from NASA of the average global temperature from the early 1900s by decades. So you can see from 1900 on the top left-hand corner going across the slide, all the way down to the bottom ones, which are the last 2 decades. And the darker areas here are warming temperatures. So you can see the very clear indication that the world is getting warmer. And the most interesting bit, as Peter has already said, is that the Arctic and the Antarctic are warming 2 or 3 times faster than the rest of the world. I won't dwell on that for the moment, as Peter's covered a lot of it already. What we're doing is pushing carbon into the atmosphere at rates which are unprecedented in human history, even going back to the Paleocene thermal maximum in about 55 million years ago, where there were some very major extinction events. You can see what we're currently doing on the extreme left-hand side of this slide is about 10 times faster than that so-called PET period. So we're doing things that nobody's ever seen before in the paleoclimate record. It's not surprising, therefore, that we're seeing big effects. Now, we can already see the impact of that in the speed with which national disasters are mounting. This is a picture from Munich Re, one of the world's big global reinsurance companies, which demonstrates the number of climate-related disasters going back to the 1980s. And you can see the peak in the 2018 period. If you move on to the next one, the cost of that is represented in this same graph. You can see the cost going up. The green is the overall cost, and the blue is the insured component of that. So in other words, in 2017, we had an overall loss of about $340 billion around the world. And of that, only 138 billion were actually insured, which means that the countries that are less able to carry the impact of these climate disasters were carrying the bulk of the cost directly without any insurance recovery. If you look at global temperature increase, this is a picture from the report that the IPCC produced last month only on the land use impacts of climate. And you can see in these pictures that the average global increase in surface air temperature over land, land and ocean, is just under a degree. That's the lower line on here. But that average globally, in fact, means that land temperatures increase even more. So the Paris Climate Agreement, which tries to keep average temperature toward 1.5 degrees C, we already see 1.53 degrees C on average over land. So we're already pushing the boundaries of the Paris Climate Agreement. And climate is already having major social consequences. We tend to talk of things like the Syrian war and the North African refugee crisis as basically either geopolitical issues, social issues, wartime effects and so on. But the fundamental problem is behind most of them, you have a climate driver. Syria, for example, they had the worst drought in recorded history for an extended period from about 2005, having had previous droughts before that. 60% of the population of Syria was on the land, an agrarian population. They could no longer sustain their activities, so they moved to the cities. The Syrian cities were not capable of actually sustaining that population, sudden population growth. They already had 1.5 million refugees from Iraq. So the result was that people started migrating. So you had this massive migration from Syria and from North Africa, which is having similar climate problems, into Europe. The result of that is one of the main drivers of Brexit, which we now see because of migration pressures in the European Union and the British reaction to that. If you look at President Trump's Mexican wall, we're told it's all about drug peddlers and criminals storming into the United States. In fact, most of the problem was driven by climate change in Central America and Northern South America, in countries like Honduras and Guatemala, which have already seen major agricultural productivity falls because of climate. So these things are actually already happening socially in a very major sense. Now, to come to the Paris Climate Agreement, this picture shows in the grey line the way that global historic emissions have developed. And the green, the yellow, and the purple lines show what has to happen if we are going to meet the Paris target, which is to limit temperature increase to well below 2 degrees C above pre-industrial levels, and to pursue efforts to limit it to 1.5. So it means that emissions have to peak very rapidly and then drop steeply in the way you can see here. And the longer you leave it before they peak, the steeper the fall has to be to stay below 2 degrees C. And this is 2 degrees C, not 1.5, okay? Now, unfortunately, the path we're currently on is actually the red line. The top line you see there are business as usual. We're still on that path. The Paris commitments, as opposed to the targets, but the commitments that were made in December 2015, if they were all implemented, will lead us to the orange line. Now, that line doesn't see any reduction in emissions. It just means they level off by 2030. And that's nowhere near good enough. So what it means is there's a yawning chasm between the rhetoric of Paris, which regarded as a diplomatic triumph, which in many ways it was, because it got everybody together, and the reality of what we have to do to meet the target that the Paris Agreement set up. So that's what we're still struggling with, and there's no sign at the moment of emissions reducing because we're going up still at worst case levels. So if I was to summarize this, what we've seen already in Paris is today a 1 degree increase in global temperatures. That's already occurring, and we're already seeing dangerous climate change of that. The Paris upper limit is 2 degrees, and we probably already have 1.5 degrees built into the system that we can't avoid because of historic emissions. The actual Paris emissions commitments will lead us to 3 degrees, and the actual path we're on today will be above 4 degrees. And that's by 2100 in theory, but possibly earlier. Now, what that means is that at 1 degree, we're already seeing the disappearance of the Arctic sea ice that Peter's mentioned, and West Antarctic ice is also reaching tipping points, probably. 2 degrees is now the boundary of extremely dangerous climate change. 3 degrees, according to some of the best national security experts in the world, will be a world of outright social chaos because of the impact of increased temperature, increased sea level, increased flooding in many parts of the world, and so on. And 4 degrees is incompatible with an organized global society, according to the same experts. That's not me talking, this is some of the best people in the national intelligence organizations around the world. In other words, 4 degrees, our current path, is global collapse, and it could occur before 2100 unless we start to do something much more serious about responding to the challenge. But the climate forcing increasing temperature is still increasing. It should be decreasing to have any chance of staying below 2 degrees C. This is just another way of showing the effect of current emissions that is produced by Jim Hansen's group at Columbia University. What it shows is the forcing on raising temperatures of all of the greenhouse gases, not just carbon dioxide. So CO2 is the lower aqua color. Then you have methane above that. Then you have nitrous oxide in the green. And then the trace gases that were the subject of the Montreal Protocol in 1989. And what you can see is that the tip is still going up. But the reason I put this up is to demonstrate another point. And that is the fact that we have a massive challenge to reduce emissions, but we have actually done it before. We did it with the Montreal Protocol, and you can see that dramatic drop in around 1990 and afterwards when the Montreal Protocol measures came into effect. So humanity has actually done this sort of thing when it puts its mind to it. Now, the problem, of course, with today is that this was a much simpler problem in 1989 because it was just the trace gases around refrigerants and so on. And there were few producers and relatively few users of the material. And so it was handleable. Today we have a much bigger problem, and so we're going to have to devote far more resources to solving it. But you would say, why is that actually happening? Why are these forcing emissions going up? When we hear all this noise about the rapid development of renewable energy and alternatives, the fact their costs are dropping, everybody is taking up solar, wind, and so on. The problem is that the development of that renewable industry has been really very impressive, but it's coming off a very low base. And if you look back at the development increase in energy over the last 10 years, from 2000 to 2016, you can see that most of the growth has been coming from fossil fuels, coal, oil, and gas. The others are starting to rise very quickly, but fossil fuel still dominates, and we have to now change that, completely reverse it. So there's an urgency to actually do this. And one of our problems, of course, now turning to the energy dimensions of this, is we still are subsidizing fossil fuels by a massive amount of money. Something just under $5 trillion a year is being spent around the world by governments to subsidize the use of fossil fuels. Now, that's including the full cost of not accounting for their climate impact. So in other words, the cost of the disasters, the health effects you get from increased pollution and so on. It's all built into these numbers, which were produced by the International Monetary Fund, which is not exactly your left-wing tree-hugging organization. I mean, you know, this is the real accounting for the cost of fossil fuels, which governments around the world have not been prepared to do by putting a price on carbon, which we should do. It's crazy not to. In other words, the fossil fuel industry are still having an enormous free kick in keeping their operations running by the fact that we don't do this. I mean, in my country alone, in Australia, that translates into 42 billion Australian dollars to maintain and expand the fossil fuel industry, which is more than we spend on the defence of the country. I mean, this is crazy stuff, but our political leaders have not been prepared to address it. We are seeing the reduction in fossil fuel building in the sense that the capacity of coal, for example, the growth is slowing down. You can see these black lines here indicate the slowing down of increased capacity and the fall in the number of units, and the black lines there. But the point is that people are still building new coal-fired power stations, particularly in Asia, and I think even in Korea at the moment. And I mean, this is crazy in a world where we have this size of a problem we're confronting. I know a lot of them are newer type of stations which are replacing older ones, but that's not good enough for reasons I'll come to shortly. The cost of alternative energy is certainly declining fast. This picture shows, it's a bit complicated, but just very simply on the left you see the on the right-hand side you see the marginal cost of coal operations, which is the cost, just the operating cost, not including the capital. On the left-hand side, you see the cost of new wind and then solar, and this is the full cost, including their capital. So you can see they are already starting to be, in many countries, below the cost of even the marginal cost of coal. So the economic incentive now to move onto these other forms of energy is now getting bigger and bigger, and people are doing it. But we have to increase that change far faster than we're currently seeing. So if I can come on now to the risk dimensions of this. The scientists are very worried about the issues of tipping points that Peter's already touched on in the Arctic. That's the disappearance of the sea ice, the exponential increase of positive feedbacks, which may lead to methane outbursts, as Peter's indicated. But there are many others around the world. The jet stream, again, Peter talked about, which is causing increased stationary systems over North America and Europe and so on, producing much longer heat waves. I think you probably experienced some of that in Asia too, in China and so on. The Amazon rainforest, the West Antarctic ice sheet. These are points where, I mean, climate change doesn't just gradually come in a steady, linear manner. You will get areas in the climate system which suddenly jump from one state, which is encouraging toward human activity, the development of human activity, to another one which is completely destructive to it, and you suddenly flip. And the concern the scientists have is that if we see these things happening around the world, it's going to produce some very nasty effects, and effects which become quite irreversible unless we find ways and means to avoid them actually happening. And the trouble is that if you get to the point where they take off, it then is probably impossible to do anything about it. So there's a real urgency to stop these things actually happening. There are one or two we can't do much about it. And they may already be triggered, but there are a lot of others that haven't yet happened. And the trouble is that these are not quantified in the reports from the Intergovernmental Panel on Climate Change, because often for good reasons we don't have enough information to really know what's going to happen. They're talked about qualitatively, but not in a quantitative sense. So we are in many ways only dealing with part of the problem. And the worst part of the problem is the bit that's being left out, which in risk terms is very dangerous, because you really always should be looking at the potential worst-case scenarios and planning for that, and trying and hoping that it doesn't actually happen, but at least you plan for it. This shows the same tipping points in a slightly different format. The graph at the bottom here, the blue-purple line, shows global temperature on average back 20,000 years. And you can see the remarkable thing about this is the last 10,000 years, that temperature has been remarkably stable, about 15 degrees C plus or minus half a degree. And that's the period in which humanity has basically developed humanity in the way we know it, the current civilizations. The temperature now is shooting up on the right-hand side there, and these green and orange figures, RCP figures, are the scenarios the IPCC puts out. The green one is staying at 2 degrees C roughly, the red one is business as usual, which we're currently headed on, and the number 6 is roughly the Paris Agreement in broad terms. Now, the actual Paris Agreement range is that grey bar, and you can see the tipping point areas are shown here in a bar which at the bottom is low risk and the top darker redder area is high risk, so the range of risk increases as the temperature goes up. We don't know exactly when they're going to cut in, but what it's saying is that even with the Paris Agreement, were we to achieve it, we are still going to see potentially a risk of those tipping points triggering and moving into irreversible change. So Paris by itself is not necessarily a great outcome, but it's obviously one we've agreed on, one we really have to try and stick to. So the choice we now have, and this is slightly complicated, but this comes out of a paper that was produced last year. We've come from a period where we've had this stable Holocene period of the last 10,000 years, as I indicated, where temperature's been very stable. Where now temperatures are heating up, the world is moving now toward increasingly unstable conditions. We now have a choice that we either stop that happening by dropping emissions and stopping that temperature increase, and we restabilize at a hotter, but at least a controllable sense. Or if we don't do it, we will move off into what the experts called a hothouse Earth scenario, which may be an extremely unpleasant one. And we have to take all the measures we possibly can to avoid that actually happening. So, if you look at risk, one of the problems of a lot of these scenario work is that it tends to be a bit theoretical. 2 degree, 1.5 degree, what does it really mean? What is not talked about anywhere near enough, in my view, is the hard-nosed practical impact of what this actually might mean. And in a recent paper, we tried to do that in looking at a 3 degrees C scenario which might develop by 2050, quite possibly, from what we currently know, unless we move to far more rapid action. And the sort of things that might happen is we see ecosystem collapse in coral reefs around the world. It's already happening in Australia with the Great Barrier Reef. The Amazon rainforest, you've heard a lot about that in recent time with the activities of the new Brazilian president. In the Arctic, Peter's discussed. Many parts of the world we see deadly heat where greater than 100 days a year it is impossible for humans to operate effectively. And we have extreme flooding in many regions in contrast because of increased rainfall of precipitation. Sea level rise, which might be above 0.5 metre. Many nations and regions become uninhabitable because of those extreme conditions, and particularly in the Middle East, for example, and parts of Africa. Possibly 1 billion people either displaced either within countries or between countries because of these events. Major drop in crop yield and food production. The lower reaches of many of the big deltas like the Mekong, the Ganges and the Nile become inundated with effects on food production, obviously, which they're critical production centres. Major cities around the world, such as Chennai, Mumbai, Jakarta, parts of China, Hong Kong, Shanghai, and so on, Manila, Bangkok, Lagos, have to be abandoned because of encroaching seawater, and you can really hear that in Jakarta in plans to move the capital. That's not just due to climate change, it's also withdrawal of groundwater. And the potential for this hot ice Earth that I talked about being triggered earlier on. So these are the hard-nosed things that people need to understand, and politicians have to understand, particularly, and decision makers. And I think it's true to say that they haven't been prepared to honestly come to grips with that, and still aren't today. So I think the climate meetings that are going on in the near future hopefully are going to start talking more and more about these sort of realities. Now, what do we have to do to stay below the Paris limits? Well, the first thing we've got to do is stop emissions growing, and that means stopping fossil fuels, full stop. So how do we do that? Well, if you look on the left-hand side here, all of the fossil fuel resources in the world are represented by these pictures. The orange oval represents all of the resources we know about of fossil fuels. That's what we know exists. The next ring, the smaller one, the red one, are reserves. That's that part of the resource that we know can be produced technically and economically under today's conditions. And then the smaller oval, which is purple, is the part of the reserves that we're actually producing from today. So in other words, this is the oil fields, the coal fields, the gas fields that are actually under production. Now, if you just took that smaller oval and you converted that into carbon, follow the blue arrow, you would end up with that amount of carbon emission when that material is actually burnt. And you can see I won't get into the scale particularly, but you've got coal, oil, gas, and so on all shown in there. Now, if you said, well, okay, we're happy to accept 2 degrees C temperature increase, how much could we burn? It's the middle green bar. Now, that means that only 80% of the existing reserves that are being produced today can actually be produced and used. The rest have to stay in the ground. If you take a 1.5 limit, then the limit is even lower. So we can only actually use about 34%, I think the figure is, of the actual current operations. Now that means to stay within the Paris Agreement limits, there's going to be a large number of so-called stranded assets around the world, which companies, oil and gas, coal companies, are now going to have to write off because they can't produce them to stay within the Paris limits, which is going to mean big changes in the stock market and the way those companies are looked at. And obviously that's not something that people have been very happy about taking those decisions. However, what you're seeing is investors are now saying the risks of climate change are now so great that we want you to start looking at this and writing off some of those reserves. It hasn't actually happened yet, but it's going to. You're starting to see the first signs of that around the world at the present time. But part of the problem with that previous analysis is that the assumption is that if you hit 2 degrees, you only have a 66% chance of doing it. And if you hit 1.5 degrees, the chances are 50-50. That's the way the IPCC does their analysis. Now, what we're talking about here is the future of humanity. I mean, this is what it means. If we don't manage to stay below 2, then we won't have a human civilization. So that's not a very good odds, if you like. I mean, you wouldn't get on a plane to fly to Australia with a 50-50 chance of getting there. You expect to have a 99.9% certainty. So why are we prepared to play with the future of humanity at such low odds? Now, this graph shows that the blue line is the probability density function of staying below 2 degrees C. And the bottom shows that if you move from 0 to 100%, then the emissions you can put into the atmosphere reduce on the left-hand scale here. So what it says is that the emissions so far are the grey bar since the Industrial Revolution. If you say I want a 33% chance of success, then your vertical line at 33 brings you across to about a 1200 petagram emission budget. You take off what we've already emitted, so you get the little green bar, green arrow there, which is the amount we can put into the atmosphere from now on to stay below 2 degrees C. If you don't think that's very good odds, you move to 50%, and so the arrow reduces. And 66%, even a smaller amount. But if you were to say, take a sensible 90% chance of achieving that outcome, then you can see you actually have no budget left at all today to achieve that. Now that means that we should shut all fossil fuel operations down today. No more. The problem, of course, is that simply won't happen. We're addicted to fossil fuels, and therefore it's not going to happen quickly. But it does mean that we have to move with far more urgency to achieve this outcome than people are currently showing. Okay, so what I've said is climate is really an immediate existential risk. So what does existential actually mean? What it means is a risk posing permanent, large negative consequences to humanity, which we can never undo. This becomes irreversible. An adverse outcome that will either annihilate intelligent life or permanently and drastically curtail its potential. So that's what we're dealing with. And that's what people have not been prepared to talk about. And in my view, this is one of the biggest challenges we've had in climate change. Unless we honestly talk about what it means, you will never get people to face up to the urgency for action and the extent to which we actually have to change things. So why is the risk existential? Okay, well, firstly, dangerous climate change is occurring at 1 degree C, we've already seen. Secondly, to stay below 2, we have to stabilise and peak by 2020 and then come down rapidly. And 1.5 implies even greater reductions. But we're still seeing emissions going up in the worst case. Thirdly, the carbon budgets are unrealistic. As I've said, at 90%, there is no carbon budget left today. Fourth, climate inertia means that by continuing fossil fuel investments today, you are locking in outcomes you're not going to see for 20 or 30 years in the future. So what we're seeing today is the result of what emissions we put into the atmosphere over the last 30 years. And by the time it becomes clear what those implications are going to be in terms of the extreme impacts, it's too late to do anything about it. Now, sensible risk management means you act before the event occurs to stop it happening. It doesn't mean you leave it until the last minute and then try and do something about it. The other problem we have is that when you burn coal and oil, you put into the atmosphere little atmospheric aerosols. These are little particles produced from the coal and so on that float around in the atmosphere for short periods, but they have the effect of actually cooling the planet by about 0.3 to 0.5 degrees. Now, as you clean up your act in terms of getting rid of those coal and oil and so on, those particles will disappear, which means that there will be a temperature increase, a one-off temperature increase of that order. It's a bit hard to say exactly how much, but it'll be of the same order. So what we have then is a further problem because that is locked in by virtue of us having to clean up the act, which further compounds the problem. And then finally, the Paris solutions rely on so-called negative emission technologies to remove carbon from the atmosphere. Peter's talked about some of them, and there are others like carbon capture and storage we've been trying to make work at scale for a long time, unsuccessfully. The trouble is these technologies are non-existent at scale today. They exist in small operations. And if you assume that we can leave any major changes another 10 or 20 years, and that these technologies will be suddenly appearing to save us, then that's a complete, in my view, abrogation of responsibility, because it creates a false sense of security that there are easy solutions when we actually don't have any. So we need to recognise what is going on in this game politically, which is frankly misleading the global community. So why is the risk immediate? In other words, by that I mean we have to act today. We don't have 10 or 20 years. Well, first we have no carbon budget, realistically, to stay below 2 degrees C. Second, by continuing fossil fuel investment, which is what we're doing, we're locking in irreversible existential outcomes, which we won't be able to reverse. Sensible risk management means addressing risk in time to prevent it happening, as I've said, and that time basically is now. So we have to have an emergency response. We can't keep going in the way we've been doing with gradual incremental changes that are not going to deliver anywhere near the type of change we need in the time we need it. So what are the basic steps to solve this if we move on to solutions? Well, firstly, we have to accelerate innovation on low carbon alternatives. We've got to ban investment in new fossil fuel capacity from 2020, and then phase out coal, oil and gas as alternatives become available. Do it as quickly as we possibly can. We must remove the subsidies to fossil fuels. We must tighten control on fugitive emissions. These are the emissions that escape into the atmosphere from particularly things like gas operations and coal seam gas and so on. If you get much more than 3% leakage in a gas operation, it's worse than coal. And that is the reality in many parts of the world. We have to accelerate electrification to eliminate fossil fuel by 2040. We've got to redesign agricultural practices to maximize the sequestration of carbon with soil carbon, ocean sequestration and reforestation. We need a very strong emphasis on the demand side of energy, not just the supply, on conservation and efficiency. We need to encourage debate in the reframing of societal values toward evolution of sustainable societies in terms of supporting this transition. So we need new forms of economic concepts that reflect the real cost of whatever it is we're doing, not just ignoring them in the way we do at the present time under the current economic paradigm. And the immediate priority, has got to be the banning of fossil fuels. And there was another one which should have been on the end here, which is basically to establish what I call a just transition process, so that the people who are going to be worst affected by these changes are encouraged to make the change. I mean, the worst thing you can do is just to say, well, we shut down industries and leave it to everybody to sort out their own problems. You really have to retrain people, relocate them, encourage them to make the change, and get their commitment to actually making it happen. So, just to bring it to a conclusion, as Professor John Schellenhuber, the founder of the Potsdam Institute for Climate Impact Research, has said, when we're now reaching the end game with climate, where very soon we have to choose between taking unprecedented action or just accepting that it's been left too late and that we bear the consequences. And that's very much the point we really are at this stage. I mean, just to conclude this talk, I think this is a fairly disturbing picture. But the fact is that we haven't been prepared to talk in these terms historically. We tend to go off into minutiae or into the detailed scientific facts and so on, but we don't talk about the real hard-nosed implications of what is now happening. And that's been one of the biggest mistakes, I think, in the climate debate. But the fact is that the solutions are now available technically, and we're seeing day by day newer ones emerging, and Peter's touched on some of them already. What we don't have is the political and corporate will to actually now force the pace of change. And maybe it is too hard for our existing political systems to do that. What is starting to emerge, of course, as you may well know, is the community response now in terms of increased civil disobedience is starting to become a major factor in many countries. I'm not sure what's happening in Korea, but on Friday, all of the schools in Australia are on strike for climate. We have groups like the Extinction Rebellion, which are now shutting down cities, demanding action on climate. We have something more, I think, than 1,000 organisations around the world who've now accepted the need to declare a climate emergency, and that ranges from the UK, Irish, Scottish and Welsh governments right the way down to local governments. I think all of that encompasses somewhere around 300 million people at the moment. Now, in the end, I think what is going to happen is that the community pressure is going to be a major issue in forcing the political and corporate leadership to completely rethink the way they're addressing this problem. It needs to happen very fast because we don't have very much time. So the more that can be done, I think, to encourage these sort of changes within the Korean and Asian context, the better. Because a lot of investment is still going, in Asia is still going into fossil fuel expansion, particularly into power generation, which is going to be an asset that will be there for another 40 or 50 years. So you're locking in a carbon consumption path for long periods of time, unless you accept that the asset will have to be written off long before its use is finished, which is probably what's going to happen. So I think despite the fact that it's a confronting position, we do have solutions and we know the way forward. It's now a matter of triggering those sort of changes in ways that are going to be really effective rather than the completely ineffective way we've seen it for the last 30 years. So thank you very much for your time.
다시 한번 이한던우 연사님에게 뜨거운 박수 부탁드립니다. 잠시 후 학생들과 함께하는 포럼을 위해 잠시 자리 정돈이 있겠습니다. 잠시 후 다시 뵙겠습니다.